Thank you, Max, and I'd like to thank the organizer also for inviting me. And sorry for having the old Tel Aviv University logo for anyone who noticed that. Okay, so before talking about capacity for multi-user channels, zero capacity for multi-user channels, let me tell you a little bit about single-user zero capacity. So this problem was originally considered by Shannon, and he asked the question of what is the maximal rate of reliable communication over a discrete memberless channel when the constraint is that the decoder needs to reconstruct the message without any error, not with vanishing error. So let's look at this problem through an example. Here is a noisy channel over an input alphabet of 5 symbols, 1 through 5, and an output alphabet of 5 symbols, A through E. And there's an edge between an input and an output if this transition is possible. So in the zero-error regime, we only care about what can or cannot happen. So we don't care about the probabilities themselves, only whether they're 0 or non-zero. So 1 can go to A and B and so on. So what is the zero capacity of this channel? If you just have one use of the channel, then obviously the best you could do is something like use your codebook, use a codebook of 1 and 3, say, which do not overlap at the output. And if you add anything else, you might make an error. So this is the best you could do with one shot. So the zero capacity is at least 1 bit per channel use. Another way to view this, which is a little bit more basic, is using the confusion graph associated with the channel. And this graph has a vertex set that corresponds to the input alphabet. And 2 input symbols are connected by an edge if and only if they can result in the same output. So for instance, 1 and 2 are connected because they can both result in the letter B. It's not very difficult to convince yourselves that everything about the zero capacity corresponds only to the graph. So you only need to know this confusion graph. That's all that matters. And many channels have the same confusion graph. So we better study this more basic quantity. So you can think about this as the graph capacity, the capacity of associated with this graph. Now, if you highlight those 2 code words that we used, 1 and 3, on the confusion graph, then you notice that they form a maximal independent set. And this is exactly what you want, right? So for any graph with one-shot communication, you can achieve at least a rate of log the alpha of g, where alpha of g is the independence number of the graph, the size of the maximal independent set. Of course, there is no need to use the channel just once. You can use it many times. So you can look at the product channel, which corresponds to a product graph. And what is this product graph? It's a graph with vertex set of sequences of input symbols. And 2 sequences are connected by an edge if and only if every coordinate they're either equal or adjacent in this baseline graph. So this kind of graph product is usually called the strong product or the end product of a graph. If you code over this graph, then obviously what you can get is you can code over a maximal independent set of g to the n. So you can get to a rate that is 1 over n log the size of the maximal independent set of g to the n. And it's not very difficult to prove that this is actually the best you can do if you take the limit as n goes to infinity, and this limit exists, and so on. However, this is an asymptotic formula, and it turns out that alpha of g to the n can grow strictly super multiplicatively, and it's quite difficult, or generally currently impossible, to characterize this limit for any graph. Specifically for this pentagon graph, the capacity is actually half log 5 and is attained by a codebook with n equals 2. The achievability was shown by Shannon in '56, and it took about 20 years to show the converse result by LOVÁSZ, which we will discuss in a few minutes. So this talk is mostly going to be concerned with upper bounds. So let me give you a general recipe for how an upper bound on the zero capacity works. It's very simple. Here's the procedure. First, you start by finding a general upper bound for the independence number of a graph. So let's say you find some f of g that always bounds the independence number of a graph. For instance, this f of g could be the vertex click covering number of the graph. This is always an upper bound for alpha of g. Now, once you have this, you might want to check if that f of g that you have happens to be submultiplicative with respect to this product of graphs. So whether f of g to the n is upper bounded by f of g taken to the nth power. If this happens, and this happens for click covers because products of 2 clicks is a click, then you easily get that alpha of g to the n is upper bounded by f of g to the power of n. and you got yourself a single letter upper bound. The zero capacity is upper bound by log of this f of g. And of course, the whole idea here is how to find this good f of g, right? This is the part that is difficult. And basically, most known upper bounds, at least those known to me, follow this recipe in some sense. And here is a maybe partial list. So we have this log click covering number that we just mentioned. There's a feedback zero capacity result by Shannon that also provides a tighter bound. The matrix rank bound by Hammers, and most prominently, the LOVÁSZ-TYPE function, which uses SDP relaxation, which we'll discuss in more detail in a few slides. Now, as I mentioned, the zero capacity in general is unknown. It's even unknown in very small examples, for most notoriously maybe for the cycle over 7 vertices. But the study of the zero capacity led to many interesting ideas, most notably probably the SDP relaxation idea of LOVÁSZ that is used extensively in combinatorial optimization, the idea of perfect graphs and the perfect graph theorem, connections to graph entropy, Sperner capacity and its application in external set theory, and many others. So with this in mind, let's proceed and discuss multi-user zero capacity. And of course, it seems, and it is, hopeless from the outset to actually get anything tight in this setup, because as a special case of everything I'm going to present here is the single user case, which we don't know how to solve. But hopefully I will be able to convince you that the richness of the problem is when we introduce multi-user gives rise to interesting quantities and requires some new ideas and techniques. So I'm going to discuss two very basic models, the broadcast channel and the multiple access channel, the most basic multi-user setups, and discuss some recent work. And I'm not going to have almost any proofs, but most of the things are going to be pretty simple, I think. So let's start with the broadcast channel. So here's the broadcast channel, has one transmitter, X, and two receivers, Y1 and Y2. And the transmitter, and they're connected over a channel, a discrete memory channel, P of Y1, Y2 given X. The transmitter would like to convey two private messages to each of the receivers at rate R1 and R2 over some n uses of this channel. Now, the Shannon capacity, namely the vanishing error capacity of this channel, is known in many cases, not for all cases, but in many cases. But we're interested in the zero error capacity region. Namely, we're interested in characterizing all the rates R1 and R2 that are achievable under this constraint that both receivers decode their messages without any error. Now, if you think about it a little bit, you realize that all that matters here are the marginal confusion graphs that are associated with the receivers. So Y1 sees a graph G1 that corresponds to the channel from X to Y1, and Y2 sees this graph G2 that corresponds to the channel from X to Y2, and the joint distribution doesn't matter. So basically, we can think about the capacity region, the zero capacity region here, as the capacity region of this pair of graphs G1, G2. So what is known about this problem? This was actually studied by Weinstein in 2011, and what he showed, he was able to exactly characterize C of G1, G2 in three very specific cases. The first is when G1 and G2 are both disjoint union of clicks, which basically corresponds to deterministic channels from the input to both receivers. The other two cases are when G1 is a complete graph minus a click, and the other graph is either empty or the complementary of G1. It should be noted that in the first case, the capacity is actually equal to the Shannon capacity. And this can be actually deduced from other very old result by all these people. And the capacity in the other two cases is actually the worst that could be. It's just obtained by time sharing between two point-to-point strategies. So while these results are non-trivial, they're very specific. So what are we going to talk about? We're not going to limit our graphs so much, but rather the relation between the graphs to make it more accessible. So we're going to look at the graded graphs, namely that we're going to assume that the edge set of G1 is contained in the edge set of G2. So G1 is in a sense a stronger receiver, a good receiver, and G2 is a bad receiver. So whatever G2 can do, G1 can do as well. It gets less confused. So I'm going to talk about the good receiver and the bad receiver, or a strong and weak receiver in this sense. And specifically in this talk, I'm going to even limit it a little bit more and consider this maybe canonical case where the first receiver, the good receiver, is actually noiseless. It has an empty confusion graph. So the first receiver sees the input noiselessly, and the second receiver can get confused. Okay, so this can be used to characterize other degraded cases. Now, if we consider this setup, then everything here depends only on this single graph, right, on G2. So this gives rise to a very natural quantity, which I'd like to call the row capacity of a graph. What is the row capacity of the graph? The row capacity of G2 is simply the maximal rate that it can receive and can decode with 0 error under the constraint that the good receiver gets a rate at least rho. So I'm transmitting at the rate rho to the good receiver, the one that sees the input noiselessly, and I want to maximize at rate rho, and I want to maximize the zero error rate that I can give to the bad receiver. So this is C rho of G2, and in general, C rho of G, this is a function that corresponds to the graph, looks something like this. So when rho equals 0, I'm not transmitting anything to the good receiver. I'm back at the point-to-point case, and C rho of G is that's the graph capacity of G, in the usual sense. And as rho increases, I transmit more and more information to the good receiver, then this C of rho decreases in this concave fashion, and it hits the horizontal axis at log m, where m is the cardinality of the vertex set of the graph. So at this point, I'm transmitting everything to the good receiver, but I can transmit at rate log m, and I'm not giving anything to the bad receiver. So this is how it looks like in general. Now, what I'm going to discuss now is how we get upper and lower bounds on this quantity, C rho of G. All right, so in order to actually get there, we need to define some new notion of independence. And this notion we call an independent family. It's a generalization of an independent set. And what is an independent family? It's simply a bunch of disjoint subsets of the vertex set that are non-adjacent in the graph. So basically, here's an example. For this graph, here are 3 subsets of the graph, and they're non-adjacent in the sense that there's no edge going from one circle into the other circle, right? So an independent family, we call it k-independent if every subset in this family has at least k elements. So in this case, this is just a one independent family because there is this one guy here as a singleton. Of course, we can have other independent families for the same graph. For instance, this guy here, these are only 2 sets, but this is a 3 independent family because it has every subset is a size 3. We can correspondingly define what we call the k-independence number, alpha k of G, which is simply the maximal number of subsets in a k-independent set of G. So for instance, in this case, we're going to get alpha 1 of G, which is always equal to alpha of G, which is just 3. And in this case, alpha 3 of G, because we have 3 elements in each set, is exactly 2, because we cannot have more than 2 subsets that are non-adjacent with size 3 in this graph. Now, why do we care about this creature? Well, this actually gives rise to a natural superposition coding scheme for the communication problem that we have in mind. So what do I mean by that? Let's look at this graph over here. Oh, and I should also note that one other thing I should note is that you can think about independent families in another way, which is useful in terms of graph contractions. So we can think about this. So you can think about every circle here as you collapse all the vertices in the circle into one vertex. And then you get like a graph that has actually 4 vertices. And these 3 circles are now an independent set. So this is also a useful way to think about this. So OK, so what do I mean by superposition coding? So let's look at this independent family here. What we can do in order to communicate, we can use the circles to communicate data to the bad receiver, because it can separate between them. So we can send 1 bit to the bad receiver indicating which of the circles we're using, which of the subsets. And then we can choose the input, the inside vertex, inside the circle, to send information to the good receiver that can distinguish everything. Right? So we can send 1 bit in this way, 1 bit to the bad receiver, and log 3 bits to the good receiver. So the way we described it, we just realized that C rho for rho equals log 3 is at least 1. Right? And this is actually log of, which this one is actually log of alpha 3 of G. Right? So more generally, C rho of G is at least log alpha 2 to the rho of G in general. Right, so, and it might look that this family, by the way, is better than this family because this guy here is a singleton and we can't use it. But actually, it turns out, as maybe you'll see in a minute, that actually this might be more useful. All right, so if you take the product of the graph and you do the same thing, you can just get an asymptotical formula for C rho of G. And it looks like this. C rho of G is the limit of 1 over n log the 2 to the n rho independence number of G to the n. So this follows exactly by the same argument that I did for the one-shot case, just taking products. Of course, this is an asymptotical formula, so it's not very useful for us, and we'd like to get more explicit bounds. So one bound we can get is by looking more carefully at the distribution is induced. Before that, let me just mention some naive bounds. So some simple bounds that we can get for the C rho of G. One of them is a lower bound that is simply a time-sharing bound between two point-to-point strategies. So for rho equals 0, we just get the regular capacity of the graph. And for rho equals log m, we just get 0. So we have the straight line bound that we can always achieve. And this upper bound is also trivial. The rho capacity can never be larger than C of G. And also rho capacity plus rho can never be larger than log m. This is a sum rate constraint. We cannot convey more than log m bits to both receivers. And I've highlighted log m minus rho here because it's going to appear in other bounds as well. All right, so let's get some more elaborate bounds by looking at induced distributions of independent families. So what is an induced distribution induced by an independent family? Well, here's one independent family. The induced distribution corresponds to the sizes of the subsets, right? So it's very natural. We have 6 elements participating in this independent family, and the size of the subsets is 1, 2, and 3. So our distribution is 1/6, 1/3, and 1/2. Right? If we had another independent family, in this case, the distribution would be 50/50. Same way we have click covers, induced distributions. So in this case, this is a click cover of the graph. We have an induced distribution that looks like this: 1/7, 3/7, and 3/7. And we can have another click cover and have another induced distributions. Why do we care about these induced distributions? It's because we can actually, if we think about it a little bit, we can actually code over types that corresponds to these induced distributions if we take products of the graph. And if we do that and some other arguments, we can actually prove this quite simple theorem. Actually, maybe looks better, but it's quite simple. If we have a graph over m vertices and we have some independent family f of the graph and click cover k of the graph, then these upper and lower bounds hold. And they look quite the same. They come from the same place. Let's look at the upper bound. It's a minimum over a convex combination of the trivial upper bound and this Rainy entropy of order beta of the induced distribution by the click. And the same goes here, but just instead of the distribution of the click cover, we have a distribution of the independent family cover. And this bound is actually tight for this joint union of clicks, simply for the reason that click cover in this joint union of clicks is also an independent family. And actually, the proof itself just goes by reduction to the case of this joint union of clicks. This bound is also tight for the case where the graph has more than one connected component and rho is large enough. But in general, it could be very far from tight. There is one interesting structural phenomena that can be observed from the lower bound, which is that if you take a graph, any graph, and you take a large product of it, then the optimal, if you define it properly, the optimal independent families would have to have subsets of roughly the same size. So it's like an asymptotic equipartition property. And also every subset would have to be connected. Okay, so this is a nice structural result. But we'd like to get something better. This is like a generalization of the click covering versus independence number bounds, the simple bounds in the point-to-point case. We'd like to get maybe something of a LOVÁSZ-TYPE SDP bound. So how does a LOVÁSZ-TYPE SDP bound generally work? There are many different variations of it. Let me just describe roughly one of them. So what you do is you take some matrix, m by m matrix, real matrix, that is positive definite, and satisfies these conditions. Diagonal is all ones, and whenever I and j are non-adjacent, so this is a matrix of the size of the vertex set, whenever I and j are non-adjacent in the graph, then you put a 0. Otherwise, you can put whatever you want as long as it's positive definite. And it turns out that you easily relate the independence number of G to the solution of this quadratic program with linear constraint, x transpose mx with this linear constraint, and some integer constraint. And basically what happens here, the integer constraints are just stem from the fact that x represents essentially the indicator vector of the independent set you're looking for. So of course, what you can do is you can relax the constraint here and solve this over real values. And it turns out that the bound you get from this for alpha of g is multiplicative. So you can use this recipe that we discussed, and you get a nice bound. This is the LOVÁSZ bound. The question is whether we can do the same when we want to bound the k independence number of the graph, not the independence number. Turns out that what you get is a non-multiplicative creature. Okay, so you can't use this recipe, it doesn't work. And however you twist this, at least the way we tried, this doesn't seem to work. Basically, the problem is the non-multiplicativity comes from the fact that we have these interactions within the subsets. Okay, so there are edges within the subset that did not exist before because the subset were singletons, and now they interfere with our bound. And if you look under the hood, you can trace this back actually to the fact that graph contraction and graph product do not commute. And this seems to be like an obstacle in many of the approaches that we tried. However, you can still do something. What you can do is you can write the nth product of this thing. So you look at the tensorized matrix here, and you're looking for the 2 to the n row independence number of g to the n, which is what you're after. And it turns out you get this part, which is multiplicative in a sense, together with a remainder part, which is non-multiplicative. But this remainder part, if you do your analysis carefully enough, and in the special case of vertex transitive graphs, then you can actually bound it separately. And what you get from this is this sort of almost SDP bound that looks like this. If you have a regular graph, actually works also for regular graphs, not only vertex transitive, with m vertices and degree r, and mu is the smallest eigenvalue of the adjacency matrix, then your row capacity is upper bounded by this trivial upper bound minus half a divergence between this parameter p and this parameter of the graph, r over r plus mu, where p is a solution, the unique solution of some equation. Okay, so you can get some bound. Looks like this, maybe not perfect, but you get something. If you apply these bounds to the pentagon, the channel that we saw at first, then this is what you get. This is the bound on the bottom and the bound on the top are just the naive inner and upper bound. This is the time-sharing bound, and this is this naive upper bound, sum rate bound, and just the zero capacity. And the bounds in between are inner bounds and outer bounds. The inner bound is obtained by some induced distribution of an independent family that we've tried, and you could probably improve it if you take products of the graph. And the upper bound here is this LOVÁSZ, almost LOVÁSZ SDP type bound that we have. So there are many remaining questions in this area. We'd like to characterize the row capacity, of course, for some small examples. For instance, it would be nice to get a exact characterization for the pentagon, for instance. It would be nice to see if we can get some sort of a multiplicative SDP bound. So it's not clear if this can be done, but we'd like to try. One sort of nice questions, maybe two questions that arise correspond to some structural property of this curve, okay, the row capacity curve. There are two interesting points here. One point here is what I'd like to call the free lunch rate point, if you will. This is the maximal row such that C row of G is equal to C of G. So this is the point where you can still communicate to the bad receiver at the maximal rate, but get some information across to the good receiver as well. Okay, so this is free lunch, right? So this point is for disjoint union of click, for instance, this point is non-trivial. It's something it's related to the geometrical average of the sizes of the clicks. But in general, we don't even know when this point is non-zero. Okay, so that would be interesting to characterize. Another point is what you might call the optimal packing rate point, which is the minimal row such that C row plus row equals log m. So at this point, we're actually using all the degrees of freedom of the channel. We're transmitting at the maximal sum rate of the channel. And again, for this joint union of clicks, this point is non-trivial. It's also non-trivial for when you have more than one connected component, but in general, we don't know. All right, so let me move to the other channel model, the multiple axis model. And this, I'm going to call it MAC. I'm going to say MAC many times, so whoever is not familiar with this, this is the acronym. So here's the setup. It's a dual setup to what we had. Now we have two transmitters that cannot coordinate and one receiver, and they're connected over a channel PY given X1 and X2. And each transmitter has its own private message it would like to convey to the receiver. Now the Shannon capacity region of this setup is exactly known, but we're interested in the zero capacity region, right? So we're looking for all the rate pairs R1, R2 that are achievable without any error. Now, if you think about this in terms of confusion graphs, it gets a little confusing. So what I mean by that, so Y naturally has a confusion graph over the product alphabet, X1 times X2, right? But since the users cannot coordinate, what we're actually looking for is not a maximal independent set of this graph, but rather a maximal rectangular independent set of the graph. Rectangular with respect to this Cartesian structure, right? Because everything needs to be, cannot be coordinated, so you cannot have like weird subsets, right? They all have to be rectangular. Even if you take products, everything has to be rectangular. This is quite difficult to handle with the existing techniques, it seems. All right, so what is known about this? The Shannon capacity region is trivially an outer bound. There are no other general outer bounds known, and this might be because nobody looked at this. But there's one special case that has been extensively studied, and it's like the most basic multiple access channel. We'll mention it in the end. It's the binary adder channel. There are many constructions, many inner bounds for this channel. There's only one non-trivial outer bound by Orbanke and Lee that outperforms the Shannon, the trivial Shannon outer bound. All right, so what I'm going to talk about, I'm going to present a rather general outer bounded technique, and I'm saying rather because there are some constraints, there are some assumptions need to be made. This is based on some work that we did for the binary adder channel, but it can actually be easily generalized to other channels. And the way it works is basically in 3 steps. So the first step, we take this MAC setup and we reduce it to a lower dimensional MAC setup that has a common message so that the transmitters can actually cooperate. So in the original setup, the transmitters cannot cooperate, but in a sense, they do cooperate in the sense that their 2 codebooks have to be really well aligned somehow, right? So this reduction sort of tries to capture this cooperation and bring it into real cooperation over some outer MAC. So this is the first step, and this using some notion of higher order VC dimension that I'll define. At that point, we get this new MAC, and for this new MAC, we can actually find the associated Shannon capacity region, which is given by a classical work of Slepin and Wolf and Willems. So we can actually get outer bounds for this new setup once we have removed this cooperation part and encapsulated it in this common message thing that we have. And this outer bound that we will have through Shannon theory can be translated back into a bound on the original rates we were looking for. For the binary adder channel, this uniformly proves the best known bound by Orbanke and Lee. All right, so let me talk about higher order VC dimension. If you don't know what a VC dimension is, then this is a special case of what I'm going to discuss, so it's fine. Let me define projection first. What is a projection? So if we have a vector C in x to the n, and S is some subset of coordinates of this vector, then we write C of S to be the projection of C onto these coordinates. And for example, if the vector is this binary vector here, and we're looking at projection of the coordinates 2, 3, 5, and 6, then this is what we get. Okay, we'll look at it as these coordinates. Similarly, we can define a projection of a whole codebook, right, or a subset of x to the n, onto these coordinates, right? So what we get by this is we get a multi-set of projections. So what I mean by multi-set is that if we get the same projection from more than one element, then we count it. We count the multiplicities. Okay, so we get the multi-set of all possible projections onto S. Let me define another concept of what is called K-shattering. So what is K-shattering? Look at this. We say that the set of coordinates S is K-shattered by the codebook if the projection of the codebook over S contains all possible vectors of this length S, each appearing at least K times. So for example, if this is the codebook, if the case is binary, this is the codebook, then the 6th coordinate is 2 shattered because 0 appears twice and 1 appears twice. On the other hand, the 5th coordinate is only 1 shattered because 0 appears 3 times, 1 appears only once. Okay? And now a kth order VC dimension is simply, the kth order VC dimension of the codebook C is simply the cardinality of the largest set that is K shattered by C. The classical VC dimension is simply the first order VC dimension, when we don't require repetitions. All right, so here, the first order VC dimension can be lower bounded by what is known as the Sauer's lemma and in some extensions of it. And this can be generalized actually to higher order VC dimension. For instance, in the binary case, what you get is this, what we call the soft Sauer lemma. What you can prove is this result. It says that if the VC dimension of a codebook is d-1, then the size of the codebook cannot be larger than some Hamming ball of radius t star, where t star satisfies something that relates to k. So this is what you can prove. And now let's go to the reduction and see how we can use it. So the assumption I'm going to make on the channel is that there exists a pivotal output, y star. What do I mean by that? It means that there is a y star such that if the first receiver picks any x1, the second receiver can pick an x2 to make y star possible. Okay, so it can always make y star possible at the output if we want, if the second receiver wants that. Okay, so let's say that this holds, and let's say you give me two code books, C1 and C2, which you claim to be zero error. And suppose that S is a subset of coordinates of C2 that is shattered, K shattered by C2. So let me take all the vectors in C1, all the code words in C1 that have a projection, specific projection P over these coordinates. Okay, so let's call this set AP. So by our assumption of shatteredness, there must be a set BP in C2 with size at least K, such that for any, if I take inputs from AP and BP, if the first receiver transmits from AP and the first transmitter sends a code word from AP and the second from BP, then the all y star output over S is possible. So these coordinates are not useful, right? Because you can get confused over them. So that means that the complementary coordinates must be zero error codebooks. Now this holds true for any P. So basically what you've done is you've taken the zero error codebook and you partition it into many small zero error codebooks based on this projection P. Okay? So this projection P can be construed as a common message. If you decide what is P, then you could use the zero error codebook that you like, and the receiver would be able to decode P as well. Okay, we basically your message and this projection. So basically what we showed here is that if you have R1 and R2 in the zero capacity region of the original problem, then you can get a small R0, R1, and R2 in the zero capacity region with a common message of a similar channel. Where small R0 here corresponds to the common message rate. Okay, so and this relation between these rates is given by the soft limit. Okay, now if you can outer bound the small r's, you can get an outer bound for the capital R's, which we want. And the bound for the small r's is just given by what we do for the small r's is use Shannon theory. So there is a result by Slepian and Wolf and Willems that characterizes exactly what can be achieved over a multiple access channel with a common message. This depends on this auxiliary random variable, which is typical in information theory. But this cardinality of this guy can be bounded by 4. So this can be solved. This is a finite dimensional optimization problem. So if we connect these two, we get a bound. And for instance, for the binary adder channel, it's a very simple channel where the inputs are just bits, and the output is the real sum of those bits. So we get outputs 0, 1, 2. We can use this because there is a pivotal output, y star. Y star equals 1 is pivotal because 0 plus 1 and 1 plus 0 both give you 1. As I said, there are many weak inner bounds, and the Shannon capacity is the best known except for this result over Barnkey and Lee around R1 equals 1. And if we apply what we just said, we can get this theorem that characterizes what our bound gives. And if we plot this, here's a plot of the bounds. The upper curve is the Shannon capacity bound. The curve below it is Barnkey and Lee's result. And the red curve is what we get from our new bound. All right, so many questions here, but the main question, I think, is how to use. So we haven't used the structure of the other codebook. Right, so the extremal codebooks for the VC dimension are pretty bad for communications. And we haven't used this in any sense. So for instance, if I knew that C2 was linear code, then that would have a really large shattered set, a maximal shattered set. Of course, I'm not suggesting it's a linear code, but there might be other constraints coming from the channel that would increase its VC dimension. So we don't have to take the worst case. So it's interesting to explore VC dimensions, other structural constraints for this problem. This is a quick summary of what we discussed. I'm not going to go through it. I hope I piqued your interest in this general question of multi-user zero capacity. And thank you for listening.